All right, class, so this is an ALEKS topic that's called Solving Limiting Reactant Problems in Solution, and this is a really great review topic. It's testing us on a lot of different things, so let's make sure that we can do them all. So the first thing that this thing is asking us is, it's giving us two different ionic compounds, and I can recognize those as ionic compounds because I can see that we've got barium nitrate, which is a polyatomic ion. So I need to be thinking, well, what is barium nitrate? And I've got ammonium sulfate. So again, I'm recognizing polyatomic ions, and I need to be able to, draw upon that knowledge of what those are. If you just need to look those up, that's really totally fine. As we go through the class and as you get exposed to these more, then you'll become more familiar with those. But first thing that this is testing is polyatomic ions. Obviously, it's also going to be testing limiting reactant problems, so we're going to need to take that into account as well. So let's go ahead and get started. The first thing that I would do is I would write out barium nitrate. And I'm writing BaNO3 in parentheses 2. And the reason that I'm doing that is because I know that barium should be a +2 ion. It's in group 2 on the periodic table. So if it's in an ionic compound, it will have a charge of +2. Nitrate is a polyatomic ion with a charge of -1. So I know that I'll need 2 of those nitrates for every one of those bariums so that my ionic compound here can be, can be neutral overall. So it's dissolved, so it's telling us that it's dissolved, so really that's telling us that it's aqueous, right? Plus ammonium sulfate. So ammonium is NH4 with a +1 charge, sulfate is SO4 with a 2- charge. So I'm going to need 2 of those ammoniums for every 1 sulfate. And again, this is going to be soluble in water, so it's going to be aqueous as well. And it tells us aqueous right there. So then what I need to do is I need to do a sort of a double displacement reaction to figure out what the products of this reaction might be. So the first one that I'm going to do essentially is barium sulfate. So BaSO4, and it's going to be 1 barium for every 1 sulfate, +2 charge, -2 charge. And I'll figure out if this is soluble or not in just a minute. And then the other thing that I'm going to be forming here would be ammonium nitrate. So NH4 and then NO3. And I'm putting the parenthesis there around NO3 just to really indicate that I've got 2 different pieces there. And I know that this is going to be aqueous. I know that all nitrates and all ammonium ions are going to be aqueous. But this barium sulfate, what we need to ask ourselves is this going to be soluble or insoluble? And the way that we're going to do that is really by using this data table. So this is a data table from ALEKS. So if you click on, over here, right here on this one, this is the data, and then you click on solubility of ionic compounds in water, you'll get to this handy chart here. And the way that we use this chart is we'd say, well, we're going to start with barium 2+, and then I'm going to go over to find sulfate. So where is sulfate along here? Sulfate and barium, no, it is insoluble. So this is telling me that barium sulfate is going to be insoluble in water. So we can write barium sulfate solid here. So what this is sort of telling us is that we've got a reaction here. I'm going to mix some barium nitrate with some ammonium sulfate. We're going to have a reaction, and what's going to happen in that reaction is, according to my solubility rules, I'm going to form a precipitate, right? This is my precipitate for this reaction. So again, another thing that this is testing us on. Okay, so now let's actually do the problem. I'm going to start with 1.31 grams of barium nitrate and then 150 milliliters of 60.0 millimolar ammonium sulfate. So that's the sort of annoying unit that they're giving us here, but in either case we can figure out how many moles of each one of these we're going to have. So for barium nitrate, 1.31 grams times 1 mole over, so for barium nitrate I calculate that as 261.33 grams, and that's going to end up giving me 0.005 moles of barium nitrate. And for this ammonium sulfate, 60 millimoles is going to be equal to 0.06 molar. So I'm just dividing this by 1,000. So if I want to go from milligrams to grams, you would divide by 1,000. So millimolar to molar, I'm going to divide by 1,000 as well. Then I can multiply this by 0.150, and that's going to tell me the number of moles of ammonium sulfate that I'm starting with, which is 0.009 moles. So in this case, barium nitrate is my limiting reactant. This is telling me that this is limiting, right? So it's a 1-to-1 mole-to-mole ratio, and that's why I need to have this balanced chemical equation. Let's go ahead and actually balance that, right? Balanced chemical equation. And I know that's a 1-to-1 reaction, so I know that barium nitrate is going to be my limiting reactant, and in this case, that's going to tell me essentially that my answer is going to be 0. So let's go back through that one more time. My final molarity of barium cation in the solution, that's what we're looking for. And if all of that barium cation, if that's a limiting reactant, all of that barium 2+, right? Because remember that since this is aqueous, that means that I'm going to have, so let's go over here real quick. That means that I'm going to have barium 2+ ions floating around and 2 equivalents of NO3- ions floating around. That's what this sort of means, right? So all of this barium 2+ is actually going to be removed from solution and form this barium sulfate because this is a soluble product, because this is a precipitate. So therefore, since this is limiting, all of that barium 2+ is going to be consumed. It's going to be taken out of the solution. And then, the amount of barium cation that's remaining in the solution is going to end up just being 0. There's no barium 2+ left over. There's no barium 2+ ions left over. So the answer here is going to be 0 molar. So you can just put in 0 there for a question like this. So this would be an example when the thing that we're looking for is the limiting reactant. So there's other examples. So I'll do on the next video a slightly more difficult case.